So this is our third and last lecture, final lecture on heat exchangers. We've covered the vast majority of the material. We've really covered and spent a lot of time on the overall heat transfer coefficient, used extensively in heat exchanger analysis. The other is log mean temperature difference, LMTD. It used to be a lot more popular. Actually, this book had more time and space devoted to it. But right now, all we use is the log mean temperature difference to get the rate equation, UA delta T log mean, or log mean temperature difference. Really only for concentric tube heat exchangers. They used to have this correction factor that would go in here, and then you could look up the correction factor as a complicated formula for a cross flow, mixed or unmixed, or a shell and tube heat exchanger. And actually somebody told me that one of the homework, or two of the homework problems I added required you to do that. But then there's no resource to do it. So it's a mismatch between what Wiley Plus has and the textbook has. Did you encounter that? Yeah, very frustrating. I'm so sorry about that. My apologies. We will not have those points count against you. But basically, the correction factor F is gone. You can look at previous editions of this textbook, and they had it in there. But that's gone. And now, if you really want to do something more than concentric tube, you use the effectiveness NTU method. A little more abstract, but very, very easy to use, very powerful, and they have it for all different types of heat exchangers. And this book just is limited. It just has a few pages devoted to heat exchangers. Other books, the whole book is on heat exchanger analysis and all kinds of crazy configurations. All right. We talk a lot about design issues. We'll talk a little bit more about them today. I'm going to come back and revisit you at the end of today's lecture. One thing I did do is I put up an updated equation sheet that you can use for the exam on the Blackboard Learn. Show of hands, how many people have already seen it? Okay, not as many. I uploaded it Sunday. So you should be able to get it. It's like 30-some pages now. But it has these tables in it. And so this is a snippet of part of that table. If I jump over here, here it is. This is the whole thing. You know, for table 11.3, and then I just go down and there's some more material in it, 11.4, all kinds of even plots available, etc. You need to go and get it, print it, do it double-sided, otherwise you're going to, it's going to be a lot of weight carrying it. Don't add any notes, right? It's a clean equation sheet for the exam, right? And then bring it for the exam. Any questions about the equation sheet? We want to use the effectiveness NTU method and analyze this problem. Let's take a look at it. We have a very long counterflow concentric tube heat exchanger that has hot water in at 120 and that mass flow rate, cold water, so both of the fluids, hot and cold, are water, and the water comes in the cold side at 30 with the same mass flow rate. Well, what do we want to do? We want to organize our information so that we're able to calculate the hot fluid outlet temperature using the effectiveness NTU method. So I like to make a sketch like this, put the hot fluid on one side, the cold fluid, and then be careful of which one, because it's counterflow, the hot will come in on this side and the cold come in on the other side. So 30 degrees C on the cold over here and a hot 120 degrees C. We are asked to calculate the hot fluid outlet temperature, and there's our choices to calculate it. Okay, so I've used that it's counterflow, concentric tube. What about this very long? That's a key piece of information given in the problem statement. What does it mean if it's very, very long? L is big. So if I said, what is L? You'd say it's big. Okay, well, give me a number for big. How about infinity? Big enough? Okay, if L is infinity, what is the area through which the heat is transferred from one fluid to the other fluid? Small or big? Big. It's also infinity. And the equation would be pi dl if you knew that diameter of that inner tube. Okay. If the area is big, area is related to the number of transfer units, isn't it? The number of transfer units is UA over C min. For a finite value for the overall heat transfer coefficient, they didn't give me a number for it, but let's, 550, whatever it is. And then finite value for C min, they didn't give me a number, but it's a finite value. But if I multiply that by infinity for A, what is the number of transfer units equal to? Big infinity. Okay. So that's for a very, very long heat exchanger. So now I want to calculate this outlet fluid temperature. What equation would I use? I'd use an energy balance for the hot fluid. Okay, the energy balance for the hot fluid is the heat capacity rate of the hot fluid times temperature hot in minus temperature hot out, right? So temperature hot out, rearranging, is equal to temperature hot in minus Q divided by the heat capacity rate of the hot fluid. Maybe if you've solved a few problems, you've used that over and over again. The key, what's new for this class, is how to get U, not U, how to get, U also, but how to get Q. So we use the rate equation to calculate Q. Using the effectiveness NTU method, what is Q? That's where I'm going to pause, and I want you to pick up this solution and make some notes on your piece of paper, because we're going to play with this problem and revisit it and revise it and revisit it and revise it for the next 10 or 15 or 20 or 30 minutes, okay? So this is where I want you to pick it up and see if you can't deduce what is that hot fluid outlet temperature. All right, so I'll pick it up here for a minute or two. We do want to use the effectiveness NTU method. Some people wrote LMTD, wrong approach. We're going to get effectiveness times Q max. That's the rate of heat transfer. And once I could calculate that Q, I would stuff it into this equation and then let me calculate T hot out. Okay, well, how do I get either the effectiveness or the number of transfer units? Well, the effectiveness comes from the relationship for the type of heat exchanger. So I'm going to say that one of these three equations, equation A, B, or C, out of table 11.3 is the equation that we need for this problem. So hopefully you made some good notes. What kind of problem is it? Right? And now I'm going to say either equation A, B, or C. So I'm glad to say that nobody selected A, which is good because this is a counterflow. But you had two choices. Now, way over here is what distinguishes between choice B and C. And so what is C sub R? That's the ratio of the minimum to the maximum heat capacity rate. For this problem, it was both water on both sides at the same flow rate. You assume the same specific heat, same flow rate, guess what? It's 1. C sub R is 1, so which one? It's C. Let's grade it. And 72%, we're good. Now, I'm going to say that I'm going to keep going back to this equation because in a minute I'm going to need B. I'm going to need that other equation. Or I'm going to need A, okay? So instead of me continuing going back, I'm going to encourage you to find it on a laptop, cell phone, equation sheet that you printed out. Otherwise, I got to keep jumping back. I may end up jumping back and forth anyway. But, okay? So that's the equation. So we come over here and you say, what was it? The effectiveness was equal to the number of transfer units divided by 1 plus the number of transfer units. Number of transfer units, we just agreed, went off to infinity. So it's infinity over 1 plus infinity. The choice is, does that mean the effectiveness is either 0, 1, or infinity? Another clicker question. Answer A, B, or C. Well, let's take a look at the results. So a lot of us said that it is 1. Are they correct? Yeah. Maybe some of you were thinking also a plot you plot effectiveness versus NTU. NTU goes from 0, 1, 2, all the way out. And then effectiveness goes between 0 and 1. And we have a lot of times some red lines like this or orange lines like that. And usually the highest is the C sub r is 0, and then the lowest is C sub r equal to 1. But they could approach 100% for effectiveness. It's not like they ever go off to infinity for effectiveness. And they usually, unless an NTU is 0, the effectiveness is above 0. So this is the best option right there. So let's finish that. So we've cleaned this up. And so it's 1. Okay, then that's 1. What is Q max? I got to go over here. What is Q max for this problem? Isn't it C min times T hot in minus T cold in? Yeah. At this point, we're ready to substitute into this equation. And so we have that the temperature hot out is equal to the temperature hot in minus Q. I'm going to put C hot, T hot in minus T cold in, divided by C of the hot. What cancels? Heat capacity rates of the hot. And now we just have this T hot in minus T hot in plus T cold in. T hot out is T cold in. So, what was our best answer? Oh, I didn't ask the clicker question, did I? Oh, well, I spoiled that one. Was there? No. You want one right today, don't you? Okay, so what is the correct answer? 40. Oh, okay, sure. It's 30. And maybe if you wanted to, you go back and you plot. Engineers like to make plots of temperature as a function of length L, or X, and X goes all the way out here to L, but this is some sort of infinitely long. And we started with the hot up here, and we started with a cold over here, and basically the hot is going to go down and exit at the cold, and the cold is going to go up and exit at the and because it's infinitely long, theta, the temperature difference anywhere within that heat exchanger is small. It's like 0.001 degrees C temperature difference because you have all this area to drive the heat transfer. It leads a small theta temperature difference. So we really understand that. Then guess what we do? Change the problem a little. All right, so now we change it, and what did we change? It's now parallel flow. So maybe we go back and we have a sketch, and we're going to plot temperature, and we'll put the temperature hot in at 120 degrees C, temperature cold in on the same side now, because it's parallel flow, is 30 degrees C. What is going to be the hot fluid outlet temperature? So way over here, what is the temperature hot out? It's concentric tube parallel flow. I'm going to give you a few minutes to work on it. We want to use the effectiveness NTU method. A lot of the pieces of the puzzle we can recycle or use from the previous problem, but we have to adapt it a little bit, okay? The hot fluid has the same heat capacity rate as the cold fluid, doesn't it? So it's not like one is really blowing through the heat exchanger and dominating it and acting like a thermal sink. No. And so basically if the hot's changing, the cold is also changing. And they kind of do this exponential where they come out at the same temperature, don't they? And the same temperature probably is 75, halfway between. You add the 30, 120 divided by 2, 75. Let's see if your intuition for a lot of us is correct, right? Let's do it with the math. So we have the energy balance gives us the equation like it did before. The temperature of the hot out is equal to the temperature of the hot in minus Q divided by the heat capacity rate of the hot fluid. What is that equation? Where did that come from? Energy balance from the perspective of the hot fluid. Okay, we then come to Q is equal to the effectiveness times Q max. For this problem, the Q max is equal to C hot or C min, they have the same heat capacity rate, times the temperature hot in minus temperature cold in. I have to get the effectiveness. Okay, so I look for in a relationship for the effectiveness as a function of number of transfer units, etc. I'm going to write it out. It's 1 minus the exponential of the negative of the number of transfer units times 1 plus the ratio of heat capacity rates close. And then we divide by 1 plus the ratio of heat capacity rates. Do I have to memorize that, Professor, for the exam? No, come on now. We got this. What did I just write? Did I write this equation? I hope I did. That's what I intended to write. True? You follow me? Okay, so let's jump back here. So now what we're going to do is we're going to say the number of transfer units is infinity. So we have effectiveness is equal to 1 minus the exponential. We've done this before. Negative infinity times 1 plus 1, which is 2. But guess what? All of this goes off to 0. And then we divide by 1 plus 1. So the effectiveness comes to be 1/2. Okay, so now we can substitute into our energy balance equation, and we get that the temperature hot out is equal to temperature hot in minus Q, which is 1/2 times the heat capacity rate of the hot, temperature hot in minus temperature cold in, and then you divide by the heat capacity rate of the hot. I just substituted what this Q is. The Q is effectiveness times blah, blah, blah. Okay, so they cancel. So you're left with 1/2 of the temperature of the hot in plus 1/2 of the temperature of the cold in. Hey, that's what your intuition told you, right? It's in the middle. Okay, we're going back to very long counterflow. But what did we do to the mass flow rate of the cold water? We doubled it. We doubled the mass flow rate of the cold water. So maybe make your sketch and then think about plotting temperature. We'll put the hot way over here at 120. We'll put the cold over here at 30 degrees C. Previously, because it's very, very long, that's my symbol, so to speak. The textbooks use it as well for very, very long. That the hot goes like this and goes out at 30. That's what we found before. And the cold went like this and came out at 120 before. But now we have doubled the mass flow rate of the cold fluid. All right, I'm going to give you a few minutes to work on this. But what is the new temperature of the hot fluid going out? Use your intuition. Then use, if you have time, follow through with the effectiveness NTU method. I will definitely follow through with the effectiveness NTU method. Well, quite a few people got this correct. What happens to the blue? Does the blue go out at 120? No. Nope. Actually, all the changes on the blue. For extra credit, anybody want to work out? I'll walk around. Extra credit. You work out the exit temperature of the blue. Okay, of the cold fluid. What is the outlet temperature of the cold fluid? I didn't prepare the clicker for this, but you do it. The hot fluid still goes out at 30. All right, so I asked the question of what is that temperature of the cold on the outlet? And so somebody correctly calculated that it's 75 degrees C. How did they get 75 degrees C? Well, what came out of the hot has to go into the cold. What was our equation for what comes out of the hot? The heat capacity rate of the hot, the temperature hot in minus temperature hot out. What goes into the cold? The heat capacity rate of the cold times the temperature cold out minus temperature cold in. Did I mess it up yet, or am I still on track? But because the mass flow rate of the cold is double that of the hot, it's like I can bring this over underneath. And then what's the ratio of C cold over C hot? Isn't that 2? Or if you like to do it another way, you could put the temperature cold out is equal to the temperature cold in equal to 1/2. Oops, I need to put a plus there. It's plus 1/2 temperature hot in minus temperature hot out. I just did the algebra instead of get rid of that here. Bring this over here, C cold. So that ratio is 1/2. I then solve for temperature cold out. Did I do it okay? And then if you plug in the numbers, what do we pick up here? Do you pick up the 75? Very good. Thank you very much for those especially that got it correct. But what about this temperature of the hot out? I know that I said it's equal to 30, but using the equations, what do? Well, you have to get the right equation. We go back here, and it is counterflow, but is C sub R equal to 1? Nope. So we have to use that middle equation, don't we? Okay, now in the interest of space and time, let me just play with it here. What is the number of transfer units to put in that equation? Is it still infinity? And so the exponential of all of this, 0, exponential e to the minus infinity gives 0. Likewise down here, what is all this? 0. So I'm left with effectiveness is equal to 1. Effectiveness is 1 for that problem. Okay, maybe it takes you a little longer, but effectiveness is equal to 1. Then you C min is C hot. I don't have room here, but you run through the same equations, they cancel out, you get that it still comes out 30. The hot fluid still comes out at 30 degrees. Hold it, what slide did I jump to? I didn't get to the right slide. The hot gets out to 30 degrees C. Right? You ready to play this game some more? Very long. Parallel flow. Concentric tube. This time the cold water flow rate is 8 times the hot. 8 times the hot. We really turned up the pumps on the cold side. So what is the hot fluid outlet temperature? I'm going to pause and let you work on it. I think this has to be better, Professor. Okay, so we're going to go back to this equation, and we're going to get the parallel flow. We need to get this one, do we not? Okay. If you get that one, what is the number of transfer units equal to? Still infinity. So all of this is 0. So the effectiveness boils down to 1 over 1 plus C sub R. If the mass flow rate of the hot fluid is 8 times that of the cold is 8 times that of the hot, what is C sub R? 1/8. So, what is effectiveness? 8/9. True? Good. You had to get that. You had to get the effectiveness is 8/9. Now it's easy. Okay, so let's jump back if I can find the right sheet. So we did a lot of work. We find the effectiveness is 8/9. So that the Q actual is effectiveness times the minimum heat capacity rate. That's still the hot fluid. Temperature hot in minus temperature hot out. Not temperature cold in, sorry. And then that's our rate equation from our energy balance. Q is equal to heat capacity rate of the hot times temperature hot in minus temperature hot out, so that temperature hot out is equal to temperature hot in minus Q divided by C hot is equal to temperature hot in minus Q, which is effectiveness, C hot. You're going to divide by C hot, that's going to cancel. Temperature hot in minus temperature cold in. So it's equal to temperature hot in minus my effectiveness 8/9 of the temperature hot in minus temperature cold in. It's equal to 1/9 of temperature hot in plus 8/9 of temperature cold in. Yeah, so we put in here for the 120, we put in here for the 30 degrees, and you calculate that it's equal to 40 degrees. And if you want, you plot it, and you see a pretty dramatic, let me see if I can plot it quickly. So the hot really drops down, and the cold rises a little bit. And they need to come together. My sketch needs to have them kind of together in equilibrium because of the super long nature of the heat exchanger. Okay? All right. Well, we stopped that discussion. We start another topic. There's a lot of cross-flow heating and cooling coils out there. They're all over campus. Every building like this has multiple in them. They're used in air conditioning in the summer, and they're used for providing heat into the side of buildings in the winter. They have a chilled water line coming from the energy plant, and it goes to different mechanical rooms in each of these buildings. This building may have 4, 5, 6 mechanical rooms. Engineering building has 1, 2, 3, I think, 3 mechanical rooms. And this is a lot bigger building here. Okay, and so they'll bring in hot water, and they'll also circulate it back. So it won't go back as hot because some of the heat is transferred out of that hot water. What's it do? It's heating up air. So the cold air from the room in the middle of winter gets heated and then dumped back into classrooms like this, and it's warmer. Warmer air comes into the vent system. Okay, so that's a cross-flow heat exchanger. That's all it is. We have all the tools to analyze it. We can size it now. We can rate it now. Okay. Likewise, in a cooling coil in the middle of summer, chilled water comes in and then it goes out, returns. That chilled water is still cold when it goes back to the energy plant, but it's a little warmer than what it came out of the plant. All right. They'll talk about a different DX coil. It's also used for cooling air in the middle of summer, but the DX is for direct expansion. They don't have water. They have a refrigerant that's actually evaporating. It's called the evaporator. In your residential homes and window air conditioning systems, you have DX coils. That's another way of calling it. It's evaporator. Okay. All right. These heat exchangers can be notoriously not linear. The equations can give a shape such that it's not a straight line. So here is out of ASHRAE, Heating, Refrigeration, Air Conditioning Handbook. If you have the flow provided and you have it at 100% and you cut it to 90 or 80 or 70%, the amount of heat transfer in that the cross-flow heat exchanger, like the coil, the heating coil, the cooling coil we just talked about, doesn't go down proportionately as a straight line. And depending on some of the conditions, it can be more nonlinear. So that you need to, if you wanted to get it down to be a 10% drop in the Q for this top case, you would have to cut the flow to 50%, which it's nonlinear. And so for controls engineers, they prefer things to be linear. And so if you are in this field, you probably see plots like this where they'll say, okay, this is what we're interested in, how much heat gets into the air in our heating application in the middle of winter as a function of the mass flow rate of the hot fluid supplied to the heating coil. Okay, that profile looks like this. So what we do is we think about trying to get a relationship where we have the percent turn on a valve. So the valve could be 100% open or 50% open or 0% open. And maybe it's a 360 rotation to go from fully open to fully closed, or maybe it's 720. I don't know. It's percent open is a rotation of the stem on that valve, something like that, or pushing the depth of the plunger. Okay, well, if you could get the valve to have the mass flow rate to match such that the hot fluid would do something like this, then as you closed it by 10%, there would be a huge reduction in the mass flow rate. Huge reduction in the mass flow rate would lead to a 10% reduction in the Q. And so you put these two together and you get a better system for control, the valve percent turn or ratio or percent open, 100% open right there. And then you get it to be nice for the controls people. This used to be more important with the old school, with a lot of digital controls, and that they can control it pretty accurately. Then it's less important. You can work with nonlinear controls easier now than you could in previous. Used to be a lot of pneumatic control. You weren't so accurate as to position. Okay, so you may see something like this, so I expose it to you. What's it come from? It comes from the nonlinear inherent behavior of the heat transfer that's occurring in the coils. I have more on this in previous semesters when I taught this class. This semester I decided to try and just cap it. There it is. I expose you to the behavior, and if you're interested, go back and look at my previous lectures for previous semesters. All right. All right, you want to solve a problem? Or do you want to do this? I'm going to revisit a little bit on the overall heat transfer coefficient cap U. Take a look. Did I spend some time? I don't recall if I spent enough time on this table. Take a look at this table. We have water, oil, steam condensing, water inside of tubes, ammonia condensing, alcohol condensing, water inside the tubes, and finned tube heat exchangers where you have water in the tubes and air in crossflow. Of all of these cases listed in this table, which one has the lowest overall heat transfer coefficient? Which one has the lowest U? Yeah, the last one, the bottom one, where I have air in crossflow and I have water inside of tubes. That's a very common application. Okay. Now, why is this the low of the low? Well, this is my next question right here. I have a cross-flow heat exchanger used to cool air. So I have water inside the tubes, okay, and air flows on the outside of the tubes. Fins are used on the air side to promote the heat transfer on the air side, yet the overall thermal resistance is still dominated by the air side. With that, I want you to write an equation for U. Write an equation for U. It's no numbers, it's just in symbols. You have to participate. So what I was looking for is 1 over UA, 1 over HA, maybe on one side, let's say the inside, plus some sort of fouling on the inside. The book uses that notation, so I'll use it right like that. And then we have L over Ka. What does that represent? Conduction through the wall of the tube. You could use the natural log of d outer over d inner divided by 2 pi kl. You could do that too. And then you have the resistance fouling on the outside, area outside, and 1 over HA on the outside. That's all I'm looking for. Now, for this problem, if it's dominated, the resistance, the overall thermal resistance is dominated by the air side, which of these 1, 2, 3, 4, 5 terms on the right are negligible? So the whole idea is that only one term dominates it. It's the air side, not the fouling on the air side, not the conduction, not the fouling on the water side, not the water side. And so what I was trying to get you to do is 1 over UA is equal to 1 over H on the air side area. Or you can get rid of the areas. It's all dependent on the H on the air side. What you try to do is you try to boost the area by doing what? Adding fins. Fins, fins, fins. They don't change the H. They just give more area for the H to take effect. So you often see radiators and other things where it's finned on the air side. Okay, that's a major theme. Please don't leave this class without that idea. Now you can answer another question. So for the same type of heat exchanger, it's dominated by the air side. How will the overall heat transfer coefficient change? Will U change by increasing or barely change or decrease if the mass flow rate of the air is increased? The mass flow rate of the air goes up. What will happen to you? And we'll take your clicker responses. All right, so the area is kind of fixed right here. Area is a constant. And you have this approach speed v. If m dot goes up, what does the velocity of air approaching that heat exchanger do? Doesn't it go up? All right, what is the Reynolds number of the air? Maybe it's external flow over the fins. Think of the previous chapter. What does the Reynolds number do? Because the velocity of the air went up, it increased. It goes up. All right, then we recall, we're interested in heat transfer off of that surface. Nusselt number is some constant, Reynolds to some power, Prandtl typically to the third. That N up here, for external convection, maybe it's 0.6, maybe it's 0.8, it's something like that. But if Reynolds number goes up, what does the Nusselt number do? It goes up. The Nusselt number goes up. All right? If the Nusselt number goes up, and the Nusselt number is defined as H times some L length scale divided by K. Let me kind of go over here. H is equal to the Nusselt times K over L. If the Nusselt number goes up, what does the H do? Goes up. And if U is proportional to H, Professor, I thought you said 1 over U is proportional to 1 over H. Isn't that the same? It's the same. So if H goes up, what does U do? Goes up. All right. Now, this is a crazy question. Maybe it's the last question. If the mass flow rate of the water inside the tubes changes, what happens to U for that heat exchanger? What heat exchanger? The heat exchanger we've been talking about, that heat exchanger. Well, what is the whole key idea here? What dominates the resistance? The air. There's barely any change. because it's dominated by the air side. Hopefully those last two things that I've left you with, this concept about the air side on these crosses, because they're all over the place, okay? And the idea of the overall heat transfer coefficient is useful, as well as this concept of nonlinearity in controls and of heating coil and emission from heating coils. With that, I remind you, we have a test next time. I'll be in my office if you have any questions, but I do have a couple meetings, so I'll only be there 5 or 10 minutes. Thank you very much.